The LLMs are essentially broken. Wait, I'm not making a bold claim here, but actually, yes. Did you noticing every next AI startup founder coming to podcast and speaking how AI will change everything? But can we just ask them, does we need that AI? The AI they're talking about are large language models, but spending a whole lot of money on large language models which are draining resources from Earth, like the American data says that it consume almost around 12% country entire forecasted power demand, which could be tripled by 2028, in which in 2023 it was 4.4. A single chat GPT query requires about 10 times more electricity than a standard Google search. And when it comes to the water, it consumes, according to the 2023 data, 17 billion gallons of water, which could be increased, of course, because some people want to make AGI. And of course, the capital investment in it, the US economy is heavily getting growth from AI because other factors are diminishing day by day. But in this video, which is sarcastically created by AI, we are going to discuss how the AI is, which we believe is not actually it is. Sounds strange, but it is. So let's see.
In 2024, U.S. private investment in artificial intelligence reached a record-breaking $109 billion, pushing development to extreme scales. But behind that financial momentum, recent research shows a problem with the brute force methodology used to build today's large language models, or LLMs, which are essentially highly complex autocomplete systems. The strategy of scaling through sheer volume is hitting a physical limit. This chart plots the core logic of the last decade, known as scaling laws. For years, intelligence was treated as a simple byproduct of scale. If you pumped exponentially more raw data and computing power into a model, its benchmark scores would reliably rise. But look at what happens at the top right of the curve. Because the Earth's physical resources are finite, that upward trajectory eventually hits a hard ceiling. The pursuit of advanced AI can no longer rely on building larger server farms. The industry is facing a crisis of supply. The first major constraint is Adina-Drocht. AI has effectively consumed the premium human internet, and training new models on AI-generated data leads to a structural collapse in the model's reasoning. Then there is the power grid. Massive training facilities require sustained peak operations and generate immense heat, straining local energy systems. Look at the industrial footprint of this power substation. The electrical toll of digital AI is physically breaking our infrastructure. Even with infinite power, developers face a cognitive constraint, the symbol grounding problem. Because LLMs only learn from text, they manipulate words based on statistical probability, without ever connecting those symbols to physical reality. An AI can generate a perfect essay about riding a bicycle, yet it possesses zero physical understanding of gravity, balance, or momentum. When an industry exhausts the world's electrical supply and text data to produce machines that still lack common sense, the machine's underlying architecture must be abandoned. To bypass the power wall, engineers are pivoting to a hardware workaround called Mixture of Experts, or MOE. Instead of activating a massive, energy-draining neural network for every single word generated, a router selectively illuminates just one specific expert pathway, while the vast majority of the network remains inactive. To solve the data drought, developers are building synthetic data distilleries. They use existing models to generate logic, which is then filtered and refined to create training material that is more concentrated than raw internet text. The focus is no longer on scraping the web for quantity. Engineers are designing efficient neural pathways to overcome the limitations of the hardware. This physical efficiency is paired with a cognitive shift. Human logic is often divided into System 1, fast, reflexive pattern matching, and System 2, deliberate, step-by-step reasoning. Traditional LLMs operate entirely as System 1 autocomplete engines. They generate the most statistically likely next word instantly, which is why they frequently provide false information with complete confidence. The industry is now pivoting to test-time compute. Instead of spending all their energy pre-training on historical text, new models are given the computing power to actively think during the actual prompt. This allows the AI to develop a hidden chain of thought. It can pause, verify its own logic, and if it recognizes a mistake, it can backtrack and try a new angle before answering. Instead of simply adding more books to the digital library, the focus is now on teaching the librarian how to critically think and self-correct. But even with verified logic, text-based reasoning is insufficient for true artificial general intelligence, or AGI, the threshold where a machine can learn any intellectual task a human can. To bridge that gap, researchers like Dr. Fei Li are developing world models. They believe that spatial intelligence, the ability to navigate 3D space, is the foundation of human cognition. To achieve AGI, models must graduate from text prediction to understanding physical laws. They need to know that if a rigid tower of blocks falls, gravity pulls it down, and the blocks maintain their physical permanence after the collision. True intelligence requires a grounded understanding of the physical laws that govern the real world. The multi-billion-dollar AI race is no longer a simple competition to hoard silicon chips and read internet posts. The stakes are moving into the physical world. This reasoning architecture is exactly what is required to safely deploy AI into physical systems, like this advanced air mobility vehicle, where a fast, reflexive hallucination is unacceptable. While human-level AGI may still be decades away, the map to get there has been entirely rewritten over the last year. AI is moving past its brute force infancy toward a future defined by deliberate, reasoning, and physical awareness. The scaling of AI training compute has reached a trillion-fold expansion, but despite this volume, these systems still hallucinate in high-stakes scenarios. The 2025 Stanford AI Index, an annual report tracking global progress in artificial intelligence, shows a clear trend. Simply adding more parameters to a neural network yields diminishing returns for actual reliability. Large language models, which are algorithms trained on petabyte-scale datasets to predict and generate text, can write flawless essays and pass medical exams, yet they routinely fail when asked to execute strict multi-step spatial logic. This chart plots standard AI benchmark scores against a specific evaluation called PlanBench. PlanBench is a testing framework that measures an AI's ability to create and execute complex logical plans. While standard benchmarks trend sharply toward 90% and above, the scores for complex reasoning remain flat. The gap between these two lines exposes the structural limit of current AI architecture. Researchers call this the System 1 probabilistic limit. Pure deep learning operates like human intuition. It relies on probabilistic pattern recognition, guessing the most likely next word based on its training data, rather than executing a deliberate deterministic reasoning process. Relying entirely on probability makes pure deep learning unsuitable for environments governed by strict rules or physical consequences. Recognizing this ceiling, AI labs are abandoning the strategy of merely feeding models larger datasets. The objective is now to build System 2 capabilities, forcing the computer to execute deliberate, verifiable logic during the exact moment it generates a response. To solve this specific bottleneck, engineers have split their focus into two distinct architectural paradigms. The first is an algorithmic approach known as test-time compute, which powers new reasoner models. Reasoner models are AI systems specifically designed to pause and calculate multiple logical paths before outputting a response. The second is a structural approach called Neurosymbolic AI. Neurosymbolic AI is a hybrid framework that physically combines neural network pattern recognition with strict rule-based logic gates. Mastering these two systems is the technical prerequisite for moving beyond statistical text generators to true artificial general intelligence. The algorithmic solution driving modern reasoner models relies on changing when the computer does its heaviest lifting. Test-time compute shifts computational resources away from the initial pre-training phase and deploys them during the inference phase, giving the model time to evaluate logic before it outputs an answer. Early attempts at this involved chain-of-thought prompting. Chain of thought is a technique where users instruct the model to write out its steps one by one to force a sequential thought process. But chain of thought falters on complex math or coding. If the model makes a mistake on step 2, that error compounds through steps 3, 4, and 5, guaranteeing an incorrect final answer, because the intermediate logic is never verified. Here, a linear 5-step logic path is evaluated by an outcome-reward model, or ORM. It scores only the final solution. If it detects a failure at step 4, the entire sequence is flagged incorrect. Valid prior work is discarded, forcing a complete restart. A process reward model, or PRM, solves this by scoring each step independently. By isolating the failure at step 4, the system retains the correct logic from previous steps, branching off a new corrected path to reach step 5. By verifying its own logic mid-generation, the model can precisely backtrack and self-correct without discarding valid reasoning. To execute this self-correction, PRMs rely on specific search topologies to navigate the thousands of potential logic branches they generate. Engineers utilize 3 primary search strategies to manage this computational load: best of n, beam search, and diverse verifier tree search, or DVTS. DVTS is an algorithm that balances exploring multiple different solutions with intensely evaluating only the most promising ones. A best of n topology evaluates parallel independent paths and selects the highest score. For complex puzzles, beam search generates diverging branches at every step. To save memory, it actively prunes low probability branches, expanding only the highest scoring nodes into the next layer. The efficiency gains are substantial. Empirical testing shows that a compact 3 billion parameter model utilizing this search strategy consistently outperforms a 70 billion parameter model on mathematical benchmarks. However, test-time compute has a strict operational constraint. It only functions when the system has the luxury of time to think, and when the rules of the environment are purely digital and unbounded. While algorithmic search structurally addresses the reasoning bottleneck for software generation, the process is too slow and structurally unsuited for the immediate, high-stakes physical world. In cyber-physical systems, waiting 30 seconds for an algorithm to search a logic tree is a catastrophic liability. Autonomous aviation and advanced air mobility, or AAM, serve as the ultimate stress test for AI reliability. Advanced air mobility is a transportation concept that integrates electric aircraft into urban and regional environments. Operating an eVTOL in a dense urban environment introduces immense kinetic risk. An eVTOL is an electric vertical takeoff and landing vehicle designed to operate much like a helicopter, but using electric propulsion. An aircraft attempting to avoid a mid-air collision cannot afford the latency of running thousands of probabilistic search branches. The aviation domain requires immediate, deterministic compliance with unbending safety standards set by the Federal Aviation Administration. The Federal Aviation Administration, or FAA, is the government agency responsible for regulating all aspects of civil aviation in the United States. The solution to this physical constraint is Neurosymbolic AI, an architecture widely considered the third wave of artificial intelligence. This diagram illustrates a neurosymbolic systems interaction cycle. A connectionist framework processes raw sensory data to make predictions. These physically connect to a symbolic framework, which applies strict logical constraints before returning refined, verified knowledge back to the model. By structurally separating perception from logic, engineers completely remove probabilistic guesswork from safety-critical flight decisions. In a real-world advanced air mobility scenario, this division of labor operates in milliseconds. To safely navigate dense, dynamic urban environments, an autonomous drone must process an overwhelming volume of sensory input instantly. The neural network's specific job is to process this noisy, high-dimensional data, which includes weather patterns, live traffic, and LiDAR. LiDAR stands for Light Detection and Ranging, a sensor system that uses pulsed lasers to measure exact distances to physical objects. The symbolic layer's job is to act as an immutable database. It strictly encodes FAA regulations, airspace constraints, and the aircraft's own physical limits. The probabilistic shield acts as a rigid barrier, enforcing strict symbolic rules. If a neural network's proposed flight path violates a mandatory aircraft separation parameter, it triggers a hard block. The shield rejects the unsafe action, forcing a reroute into a compliant, safe corridor. Aviation certification standards legally require transparent, explainable decision-making. Pure deep learning cannot provide this audit trail, but a symbolic logic gate can. Structural shielding guarantees that regulatory safety and logical compliance are enforced before an action is ever allowed to occur in the physical world. This split-screen diagram compares the two distinct engineering paradigms, the PRM search tree expanding on the left and the closed-loop neurosymbolic system on the right. While their architectures are completely different, they neutralize the exact same vulnerability, the probabilistic hallucination problem in pure deep learning. Test time compute provides the necessary verification for unbounded digital logic and software generation. Neurosymbolic AI provides the strict, bounded verification required for safety-critical environments and cyber-physical hardware. The macro trend in artificial intelligence is moving away from trillion-parameter models and towards smaller, highly verifiable systems. The goal of these technologies is integrated, deterministic intelligence that can be fully trusted. Artificial general intelligence requires engineering verifiable reasoning directly into the inference loop.